jumped around.
Yeah, I did jump around. Yeah. Okay. Well, we can talk after class. All right, so I really wanted to give a quiz to start today, but I decided not to. So we're gonna get right into this, all right? And hopefully today we'll finish off techniques of integration, and we'll be done and be ready to start into applications next time we meet. All right. So let's try and just recap briefly what we did talk about last time, because we will need this today. So you need to remember what it is that we can and can't do. And so what I was trying to get you to remember is that we kind of are building up right now a database of the types of integrals that we can handle. And that way, when we get into this partial fractions thing today, at some point we'll say, yes, it looks like that, and we'll be happy because we know how to do that. All right? So if we ever have a constant on top of a linear expression, we should be able to do it easily. It's going to turn out to be a natural log at some point. If we ever see a constant over a repeated linear factor, so we have the linear factor and it's squared or cubed or fourth power, doesn't matter what the power is, as long as it's repeated, then I should be able to handle that also. You can go look back in your notes. We did these, right, at the end of class last time. If we have a constant over a repeated linear factor, I just said that. If we have a constant over a quadratic, and that quadratic is missing the x term, we should be able to handle that. And that will usually turn into an arctan, or there's a couple of other formulas that involve x squared and a number squared. And there are formulas, let's see, formula 17 is arctan. Formula 19 is what you do when you have 1 over a squared minus u squared. Formula 20 is what you use when you have 1 over u squared minus a squared. So anytime we have a number over a quadratic without an x term, it's going to be a formula. All right? Then we saw this last time. If we have a constant over an irreducible quadratic, meaning that this right here, x squared plus 2x plus 17, is not reducible. What do I mean by not reducible? Can't factor it. I could have said non-factorable, okay? But if we have a quadratic that is irreducible and it's underneath a constant, we should be able to handle that. Do y'all remember how we did it? We completed the square. And when we completed the square, it then turned into formula 17. Or it turned into the type that we have in number 5, where you have a quadratic and it's missing the x term. All right, so up to now, that's where we are. Now, this. Okay, so we're looking at 7 now. What if we have a linear expression? And I mean linear, what I mean by linear is that x minus 1 is a linear expression, right? It's the variable x appears there. The power on that is a 1. So that's a linear expression over a quadratic expression. What do we do if we have linear over quadratic and this quadratic is irreducible, not factorable? That's what we're going to look at, all right? If it does factor, then we actually have a way of dealing with that, and that's what later today is about, right? But if this is not factorable, it's a quadratic, and this one is linear, here's the approach, okay? You ready? All right, so the idea here is that we know that when you take the derivative of something, if it's a polynomial, the derivative, the power comes down, right? So if I have a quadratic in the denominator, the derivative of the quadratic is linear, isn't it? And I have linear up here, so it's almost like I have a u down here, and the du is up here, but I'll be off a little bit maybe, yes? We're allowed to be off by a constant, yes? All right, so let me just try it. What would happen if I let u be equal to the entire denominator? What would the derivative of this be? 8x minus 4. Now, I need to put that in parentheses because it's 2 terms, and then dx. Make sense? All right, so if you were to take a 4 out, right, which you could, would it match what's over here? Okay, am I off by a constant? Is everything off by a constant? Even if I pull a 4 out. Let me pull a 4 out here. 4, I have 2x minus 1, right, dx. I could divide through by 4. 2x minus 1 dx. Are y'all following that? Is this the same as this, except off by a constant? I'm hearing yes, I'm hearing no. It's in parentheses, right? So it doesn't match exactly, right? I cannot make this turn into this, can I? By just multiplying by a number. Like if I try and divide by 2 here, I can make that an x, right? But then I have to divide that by 2, and now it's at a negative 1/2, which doesn't match this. Do you see that? I'm off by more than just a constant. If this problem up here were 2x minus 1, it would be completely different, wouldn't it? Because there we go. We have it exactly. Yes? OK. So how are we going to address this? All right. So I'm going to back up. I just did this because you all were mentioning this, right? OK. Start off, linear expression, irreducible quadratic. You make the substitution. The denominator is u. You take the derivative, and you get this here, right? We would love to have 8x minus 4 up here, wouldn't we? Wouldn't that just be wonderful if we had 8x minus 4 up there? Wouldn't it be? Because wouldn't we have du right up there, and we'd just be happy? OK, I'm going to force 8x minus 4 up there. All right, so here's magic time. Starting with the x, what do I want? 8x. Okay, how do I make an 8 appear in front of this x? I have to multiply by 8, right? Right? I mean, yes, I could just write 8. But to maintain the same problem, I have to really come out here and just be very clever and multiply by 8 over 8. Yes? That's a 1. Doesn't change the problem. But I'm going to take this 8 and distribute that 8 through. What about the 8 on the bottom? Just leave it outside. So it'll be a 1/8 now. Integral 8x minus 8 over 4x squared minus 4x plus 3 dx. Any questions? No questions? Does this match? Not yet, right? Not yet. What do I really wish I had here instead of minus 8? Minus 4. So we've done this in the past where I said that there was like a hidden 0 sitting next to something. That's what I'm going to do. I'm going to bring in a hidden 0. My hidden 0 is going to be right after the 8x. There's a plus 0, right? And guess how I'm going to write that plus 0? Minus 4 plus 4. Minus 4 plus 4. So let's just see if this works out. I'm going to try and stay up high on the board so that everyone can see this. 1/8, bless you, integral. I have 8x. Here comes my 0. I want it to be a minus 4, right? So I'm going to put minus 4 plus 4. What was already there, though, that I didn't touch? Minus 8. So I have to put the minus 8 out here. All over the denominator dx. Questions? Now, 8x minus 4 matches exactly here, doesn't it? This is more junk, though. I mean, there was a give and a take here, right? I was able to produce what I wanted, but I had to kind of compromise and be willing to put this in there also. These two together gives me what? Negative 4? OK. So if I have this 8x minus 4, and then minus 4 is what that is, am I allowed to split this right here down the middle and create two integrals? Yes. I can create two integrals. I can put this over this, then I can put the negative 4 over this, can't I? And let's just see what happens here if I do that. So I have equals, I have the 1/8, don't forget about the 1/8, integral the 8x minus 4 over 4x squared minus 4x plus 3 dx. That's one integral, right? I'm splitting this up into two integrals. The other integral is going to have what up top here? Negative 4, right? And then this on the bottom? And then what's in front of the whole integral? 1/8. Yeah. So I have plus 1/8 integral. I have a -4 over. I don't want to erase this, but just remember that, okay? Remember that? Over 4x squared minus 4x plus 3 dx. We good? Can I do anything with this -4? I could take it out, right? And then I could turn this into a, what? -1/2? Is that all right if I do that? Okay, so change that to a 1 and change this to a -1/2. All right, somebody volunteer and tell me why it is that this is actually a good thing and how you would proceed from here. Talk to me about this first integral.
Well, du now equals ax minus.
That's right. I have du up here, right? U is the bottom, du's on top. So this is just 1 over u du, isn't it? That's the way I wanted it to work. I wanted it to be 1 over u du. So that I could say the antiderivative of that would be what? Natural log of u. In this case, natural log of all that, this right here. Yes? See, this is going to be a very simple integral now, isn't it? What about this, though? I still have this.
It's a constant over.
It's a constant over an irreducible quadratic, and that's what we did at the end of last class. See, how do you do this? You complete the square. And I hate to say it, but there's no easier way around this, okay? See, this is kind of building on itself now. Y'all understand? Ethan, you're kind of squinting your eyes. You're okay with that? All right. So let's take care of the first integral. All right, let's get that out of the way. The substitution we had was u is 4x squared minus 4x plus 3. The derivative of that was 8x minus 4 in parentheses dx. That means this integral turns into 1/8 integral 1 over u du. We're all on board with that? And then that's just natural log of u. So this becomes 1/8 natural log of u, but what's u? 4x squared minus 4x plus 3. Okay, that's this one. Done with that one. Questions? Okay, this one, you said I had to complete the square, right? So let me do that over here. To complete the square, we first write out the quadratic that we're working with. I always like to say put it in descending order, highest power of x down. And then always to start, make sure what? There's a 1 in front of x squared, which we have a 4. So we're going to have to factor a 4 out. When I pull a 4 from this, what's left in here? X squared minus x plus 3 over 4. You're basically dividing everything by 4, right? Now we have a 1 in front of this. So we go through the process now of completing the square. We start by identifying the number in front of x, which for us is -1, right? What do we do with that number? We divide it by 2. So we take -1, we divide it by 2, and that's just -1 over 2. This is our first number. Remember I said that there's 2 numbers that come out of this? That's the first important number. The second important number is what? I heard someone say it. You take that and square it. So you take -1/2 and you square it, and that gives you +1/4. That's our second important number. Yeah? Then what do? Do you remember? We have a hidden 0 right there, right? Right after the x. I'm going to rewrite this with my hidden 0. But my hidden 0 is going to be what? This 1/4 plus it and then minus it. All right. Well, y'all just remind me that this is here, okay? We're working on that integral right now. for our final answer, I need to put that part right back on the front. Okay, so still completing the square here. I'm going to rewrite this line. 4 parentheses x squared minus x. Here's my new hidden 0, which was plus 1/4 minus 1/4. And then, what did I still have in there? Plus 3/4. Now, we're guaranteed that the first 3 terms will break down to be something squared, right? And what is it that it's going to be? X minus a half. And that comes from this number. So that's going to be x minus a half. And then these two have to be put together. Negative 1/4 plus 3/4 is 2/4, 1/2. So we have 1/2 here. Questions? Yes, I'm going to put the 4 in there now. What I wanted you to see is that we're going to have a double set of parentheses here. All of this, right, is still multiplied by 4, so don't forget about that. So this was the denominator, right? We went through this. This is the denominator now, right? So I will come back to this part now. I will say negative 1/2 integral 1 over. I have a 4, then I have a parentheses. Then I have another parentheses, x minus a half squared, then plus a half, and then all of that, close parentheses, dx. Anything I can do, like simple algebra here? I'm going to do u sub. I was going a little more simple than that. How about that 4? And bring that 4 out? Yes? Bring that 4 out here and make that a negative 1/8. If I bring that 4 out and make that a negative 1/8 integral, I no longer have to have that double set of parentheses. And what was the whole point of this? What was the whole point? That this would be something I can do with what? Like like a basic u substitution. If this is u, what's the derivative of u? If this is u, derivative of that is just dx. And so I can rewrite this whole integral where it'll look like 1 over u squared plus a number squared. And how do we deal with that? Arctangent, right? Arctangent. So the whole point of when you have, like on number 6 up here, when you have a constant over an irreducible, the whole point of the completing of the square is to get down here to this and to have this look like either arctan or possibly, if there was a minus here, you would have to use either formula 19 or 20, depending on how these were ordered. Right? Because wouldn't formula 19 or 20 work for this if this were a minus in here instead? What formula would we use if that's a minus? Would it be 19 or 20? It would be formula 20. Because we would have what? U squared minus a squared instead? Yes? But we have a formula for it? So that's the whole point of it. Complete the square so that you can get it to the formula and just go. We've just kind of been lucky. We've been getting arctan a lot, haven't we? That's why I told you it was so important at the very, very, very beginning of this class. It comes up a lot. All right, let me finish. So I will make a basic substitution here to finish this problem out. U is going to be x minus a half. Du then is dx. So how would this integral be rewritten if I make this substitution? Negative 1/8, what? 1 over u squared plus 1/2 du. Everyone agree? That's your formula 17. That's formula 17. Formula number 17, with A being what? Careful. This number is supposed to be A squared, isn't it? That's A squared. So isn't A the square root of that? The square root of that is just the square root of 1 over the square root of 2, which is just 1 over root 2. So A is 1 over root 2. You don't have to do this, and I'm not going to, but just, yes, this is the same as this if you rationalize the denominator, but 1 over root 2 is good enough. And I can go straight to the formula now, can't I? I have a negative 1/8 out here. And now the formula. 1 over A, isn't that what the formula says? 1 over A, arctan of U over A, right? So what's 1 divided by A for us? What's 1 over that? It just flips, just root 2. Arctangent of U over A, which is U over 1 over root 2. Right? But what was U? No, hold on. Be careful. Don't confuse this with the other U from the other integral. It's this one right here, right? X minus a half. So I've got equals negative root 2 over 8 arctangent of x minus a half over 1 over root 2. This problem's only taking 20 minutes so far. Are we good though? Do I have any questions?
I do have a quick question.
Yes.
Do we have to do the substitution for there? Can we just skip straight to 17?
I hope that at some point you just skip straight to this. The only thing I would caution you with is that if for some chance this turned out to be something like 2x minus a half, then you would have to scale by that. Because think about it. If this was 2, this would be 2, and you would have to scale by a half. That would be the only thing I'd be worried about, is that you were comfortable to the point where you just went straight to this and took care of it. See, it's a 1 here, so you don't have to worry about it. Am I making sense? Yeah. I just wanted to show it. From here on out, I won't show this step. I'll just say, oh, yeah, this is just that. Any other questions? Or so our final answer, right? Our final answer is this with that other piece I erased with the plus c at the end. So it should be, what was in front out there? Was it a 1/8? 1/8 natural log 4x squared minus 4x plus 3 minus root 2 over 8 arctangent of x minus a half over 1 over root 2 plus c. That's it. That's a lot of work, huh? By throwing a linear expression on top of that quadratic, that created quite the mess, didn't it? But it's doable.
X minus 1/2 over 1 over root 2.
Uh-huh.
Can you just write that as x minus 1/2 over root 2 instead of with the 1 in there?
The only way you could rewrite this right here is root 2x minus root 2 over 2. In other words, this flips up and becomes a root 2 on top. Does that make sense? And so you could do that. In fact, the book would probably have that inside the arctan instead of this. I don't care. I'd rather see it this way because then I can see every piece of it and I know you did it right. Do we want to check it? No. Okay, we won't check it. All right. So believe it or not, you know, this section, partial fractions, we're going to want to do something to a problem and get it to that. And once we get it to that, we're like, whew, okay, we can do that. It's going to take us 20 minutes, but we can do that, right? Now, there's an easier way. You want to know the easier way? Wolfram alpha. Oh, yeah, you can skip it, too. Yeah. Omit. Take a 0 on that problem. All right, so the last one that we have, why do I have this one in here? A linear expression over a repeated irreducible quadratic. So do you see a linear expression on top? Do you see an irreducible quadratic right there? Do you see that it's repeated, it's squared? So can we handle this? It's the same exact thing as before, right? I mean, linear over irreducible quadratic, but this time it's repeated. All right, let's try the same method. What we were really hoping for in this situation where we have linear over irreducible quadratic is that if we choose u to be the bottom, right, the derivative of it is up top. So if I let u be, I should say the bottom, but not the repeated part, just the quadratic part. If I choose this, then du here would be what? 2x dx. Do I have 2x dx? I can try and make one, right? I can try and make one. What's that? There's no, oh yeah, I forgot to write dx. Did I put it up there? Yes, I did. Sorry. Thank you. Anyone have any ideas? I could divide this by 2, and then I would have x, and I'd be pretty close, right? Except for that plus 1. Can separate. Who said that? Okay. You mean the two different integrals? So I could do this. I agree. We could do that. And then plus another integral, which would be 1 over x squared plus 1 squared dx. I could do that. Good night. Now, if I do this and split it into 2, do you agree that this one I can use as substitution, but I'm off by 2, right? So I can just scale that. So I'm not coming up with a hidden one like I did in the previous problem. I'm not forcing the numerator to be what I want it to be here. Do y'all understand I'm not doing that? Okay, so let me take this. I'm kind of out of room, so I'm going to put 1/2 du is x dx. So how would this first integral be rewritten? What would this first integral be? 1 over 2 on the outside. I'm going to keep going up here because people can't really see down here very well. So this one becomes, you said, 1/2 integral 1 over u squared du. Right, because x dx is 1/2 du. So there's your 1/2 du. And then I had 1 over u squared. And we can handle that, right? Okay. But can you do this one the same way? You cannot, right? Because if this is u, where's du? It's nowhere. You don't have an x up here, do you? You don't have an x? So I'm showing you this problem for a reason, right? I want you to see something that you haven't seen yet. Well, we've kind of seen it, but not like this. So we're good here, everyone? Yes? I want to finish off this first one at least. Antiderivative of this is negative 1 over u, isn't it? It's the antiderivative of 1 over u squared, negative 1 over u. And put those together and replace u. Just trying to get this first integral done. It would be, what, negative 1 over 2 times what? x squared plus 1. So the antiderivative of this is this. We okay? All right. But I have not dealt with this yet. I'm about to. This almost wants to be arctangent, doesn't it? It's like begging for arctangent, isn't it? Except for the squared. Squared messes everything up, right? Like if that wasn't there, we would say arctangent. We'd be happy, wouldn't we? So you think, oh, well, the squared can't mess it up that bad. Well, it does. It messes it up real bad. So, all right. Can I erase? This is what I've got to focus all my attention on now. So I'm rewriting this. Watch. Why would I do that? Why in the hell would I do that? Not arctangent because it's not, but it's trig substitution, right? I kind of realized that something squared is the same as the square root of something to the 4th power. Yeah? And now I make a substitution. X is equal to, so what do you do when you have your variable squared plus your a squared? What trig substitution do you use? X is a tangent theta. Right? X is a tangent theta, which in our case is just tan theta because a is 1, right? A is 1. So I'm making the substitution a tan theta. That means dx is secant squared theta, d theta. And then the square root of x squared plus 1, when you work it all out, which I'm not going to do, turns out to be what? Secant theta. Okay, this is all from last class, right? Last week we did this. The new part of this is that I actually squeezed a square root out of something squared. So let's rewrite this. Integral 1 over. Now this square root right here, right? This square root is secant theta, right? That's secant theta, but then raised to the 4th power. Secant to the 4th theta. Agreed? What's dx? Secant squared theta d theta. And your secant squared and your secant to the 4th, right? That goes like this, and you got a secant squared there now. What's 1 over secant squared? Cosine squared. So this integral is now integral cosine squared theta d theta. And how do we deal with even or odd, even powers of sine or cosine? Half angle identity or the power reducing. So this becomes, I'll get a 1/2 out of the formula, right? I'm always going to get a 1/2. And then integral, and then I get 2 pieces in here. It's, what, 1, and then in this case, because it's cosine plus, and then it's cosine of 2 theta. Double the angle. And can you integrate this? Yes. I know in my videos for the homework assignment for 6.2, I did that integral, like exactly this integral at least 4 times. I mean, do you see, look, this is the beginning of 6.2. This was a problem I put on the board at the beginning of 6.2. And we are now about 15 minutes into this problem, and it finally appears, right? So like I was telling you, this class builds on itself. I mean, it's just a little piece of a bigger problem now. All right, antiderivative, I'll put it up here. 1/2. Antiderivative of 1 with respect to theta. Theta, antiderivative of cosine 2 theta, 1/2 sine 2 theta. Plus some constant, right? All right. And don't forget I had that other piece out here, right? It was -1/2 times in parentheses x squared plus 1. All that was part of in my answer from earlier. I'm going to tack that on, but now I've got to get this back to x, don't I? So my substitution was was tan theta. So I'm going to do a reference triangle. I'm going to get all this information. And then we'll be done. And then we can start partial fractions. All right. So this is equal to 1/2 theta plus 1/2 sine theta cosine theta plus c. So I did, remember when I turned the sine 2 theta, it turns into 2 sine theta cosine theta? Again, I did that 4 times. Yes, but then that 1/2. Yeah, so I already distributed that 1/2 through. You don't see it? All right. So let's see. Using my information, x was tan theta. Ooh, that's nice, because I can get theta right away. Arctangent of x is theta. So I know what that is. And then my triangle looks like this. Right? And then this is square root of x squared plus 1. All right, final answer time. I'm going to bring that part that I had from the earlier part of the problem, right? Here it is. Final answer. Equal to -1/2 times x squared plus 1. Okay, that's that integral we took care of in the very beginning. And then I have this, right? So plus 1/2 theta, but theta is arctan x. And then I have plus 1/2 sine of theta. Sine of theta is this over this, right? X over the root. And then times cosine theta, which is 1 over the root. And then plus c. And I think one thing I would do to clean this up is put these roots together and then make the root go away. And then I have an x on top. Well, this one has an x on top and this one doesn't. So you could make it, and then you have a half. Yeah, we could do the half. Here, let me do it. It's -1/2 x squared plus 1 plus 1/2 arctangent x plus x over 2 times x squared plus 1 plus c. And now these have the same denominators, that's what you're saying? Yeah. So I could put those together, combine the numerators together, which would be -1 plus x. X minus 1 would be better over x squared plus 1. Then plus, no, 2x squared plus 1. Plus 1/2 arctangent x plus c. How would you check that answer if you wanted to? You do quotient rule here, right? You have to take derivative with quotient rule here, and then take derivative here, and put it all together, and hope for the best. All right. So if we see constant over linear, we're in business, right? If we see constant over repeated linear, we're okay. If we see constant over quadratic missing an x term, we're okay. We see a constant over an irreducible quadratic, we're okay. We see a linear over a irreducible quadratic, we're okay. Right? Theoretically, we're okay. I mean, we realize it's a lot of work, but it's something we can handle. Now, what is this whole section, partial fractions, about? Well, remember from college algebra the idea of a rational function. A rational function is a polynomial function divided by another polynomial function. And here are some examples of rational functions. Those are all examples. Now, whenever you have rational functions in college algebra, some of the things that we talked about were like, what's the degree of the numerator? What's the degree of the denominator? So look at the function f. What's the degree of the numerator? 3. Right. I'm going off my notes for my internet students. This is just the notes for 6 point, what is this? 3, right? So I'm looking at the examples, function f, x cubed plus x over x minus 1. So the degree of the numerator is 3, degree of denominator is 1. Okay, g, degree of numerator, 2, denominator, 3. We're all good with that? Okay. So how do we integrate rational functions? Is there a strategy for integrating? I mean, look at this. I mean, this is a freaking disaster right there. You want to integrate that? You know, I mean, that looks like a mess, doesn't it? It doesn't fall into any of these categories, does it? I mean, it doesn't look like anything we've done so far. So how do we do these in general? So here's the strategy for it. See all that? That's the strategy. All right, so this can be very complicated to read through. So I like to do these with examples because I think the strategy comes out, it's more apparent as I do examples. If I read it to you, it's like reading a math book. It doesn't make a lot of sense until you see it in action, right? So, but I will run through the first part of it. The first part of integrating a rational function is to inspect the degree of the numerator and the denominator. If the degree of the numerator is less than the denominator, we can move on to the next step. But if the degree of the numerator is greater than or equal to the denominator, we have to start the problem with long division. Then we can proceed to the next step. All right? So you ready to go after this? All right, so what I'm going to do is every problem that I had up there earlier, these functions, see these functions right here? I'm going to integrate each one of these. So we'll see how many of these we can get through today. You didn't realize you were going to be having this much fun today, did you? I hope that this class, more than any math class you've taken in the past, kind of feels like it's worth your money, because there's a lot of information in this class. All right. So we look at something like that, blank slate, we're like, okay, basic substitution? No, right? Integration by parts? I guess not, I don't know, right? Trig integral? No. Trig substitution? Do you see like square roots and things squared minus something squared? You don't see anything like that? You see how this is becoming more difficult to identify like what we're supposed to do? But it's a rational function, right? In rational functions, we should be thinking partial fractions. So my first step for this is to inspect the degree of the numerator, which we said was 3, and the degree of the denominator, which we said was 1. In the case where the degree of the numerator is bigger than or equal to the denominator, I must do long division first, right? Okay, so how do we do long division? Well, we do, on the outside of the division box, we write x minus 1, right? On the inside of the division box, we put what? The numerator, x cubed, and then we don't have an x squared there, right? So remember with long division, you need to give yourself some space for the x squared term. So 0x squared. I have an x term, but I don't have a constant term. So what I'm getting at here is when you write down the numerator, you need to account for any variables, any powers that you don't have. Give them some space because we may need to line things up here, and you need a column to line them up in. So go back to your college algebra long division notes if you have them, and you'll hopefully see something like that in there. All right, and then we normally do with division, right? Like if I said, hey, everyone, let's take 15 and divide it by 4, we say, all right, how many times does 4 go into 15? Well, about what? 3 times, almost? And then what do? We did 12 here, and then we did what? Subtract, and then that's 3, and then we continue, right? Same exact thing, except instead of looking at numbers, we're looking at variables. What do I need to turn x into x cubed? I need to multiply by x squared. So I'm going to put x squared up here somewhere, and normally we like to line them up in the x squares. It doesn't have to be. And then, just like over here, when you said 4, the next step was to multiply 3 times 4 to get 12, right? So that's what I'm going to do. I'm going to multiply this times this. But when we do that, we multiply this times each one, right? So what's x squared times x? X cubed, I put it underneath the x cubed. What's x squared times negative 1? Minus x squared. And notice I lined it up underneath the x squareds, right? Come through. And what did I do over here once I did 3 times 4 was 12? I subtracted it, which is really going to have the effect of doing what here? Changing the signs, right? So if it was positive x cubed, it's now negative. If this was negative, it's now positive. And then you add straight down. Let's do a show of hands real quick. How many of you remember seeing long division at some point in time? Okay. And keep your hands up. And you love long division. Good, good, okay. There. So you all love long division. I just looked, everyone had their hands up. So everyone's good with long division. All right, great. It's going to be good. What do I get when I add down? These are gone. I get x squared. What about over here? Just bring them straight down, right? X is here, so plus x, and then plus 0. You don't need it, but you can write it if you want. Okay, do I stop? Am I done with long division? No. I continue until I can't turn this into the first term here anymore. So can you turn x into x squared? Yes, by multiplying it by x. So I put plus x here, and then I play the same game. I take that x here, put those here. So someone tell me what I'm going to have under here right here. X squared minus x. And then I'm going to subtract, which will change the signs. I'm using a different color, but what you can do is you can like super exaggerate the sign. That way you know you changed it. If you're looking back in your notes, like that way you know something happened there. What happens when we add down now? You get 2x. Can you turn x into 2x? Multiply by 2. And now it'll become 2x. So I go 2 times x, that's 2x. And then 2 times negative 1 is negative 2. Come through and change signs. So you're sitting there in college algebra, it's like, why do I have to do long division? Long division sucks, man. Well, we need it. We need it. That comes out to be 2. Can you turn x into 2? Not really, and it's right. It doesn't have a power of x here anymore, so you're done. Really, what happens? You stop when the power on x here gets less than the power on x here. The power on x here is 1, then I can't, and this has no power of x, I can't go anymore. If this were x squared, then I would stop here when I get an x. If this were x cubed, I'd stop here when I get an x squared. All right, but this is a remainder, isn't it? In our remainder, how do we write a remainder? Like grade school like this, remainder 2. No, we don't do that, do we? What do we really write? We write plus 2, the remainder, over the divisor, x minus 1. Remainder over divisor. So what this means, okay, what this means, grand scheme of things, is that this expression, all right, is equivalent to this expression. We have not changed the problem. It's another way of writing the same expression. So I'm saying that this integral right here actually is the same as this integral. Do you believe that these are the same expressions? I mean, you could just check. You could just check to convince yourself that it works. Let's just take a number and plug it into here and see what we get. How about 2? Plug 2 in here. What do you get? 2 cubed is 8. Plus 2 is 10. 2 minus 1, 1. So 10 over 1 is 10. What happens when you plug 2 in here? 2 squared. 4 plus 2, 6 plus 2, 8, 2 over 2 minus 1 is 1, 2 over, that's 2, so that's 10, isn't it? Okay, just because that worked one time doesn't mean they're equal, but it makes us feel better that they probably are. Yes? Right? It's true. I mean, that's no way to check something is equal to do that. But I'm just trying to reassure you that, look, we haven't changed the problem, we just changed the way it looks. The integrand just looks different. And which one is better? Which one would you rather integrate? This one right here, right? This is just power rule, power rule, power rule, right? Constant over linear expression. Don't even need the sub. You could go straight to it. Watch. Antiderivative of x squared, 1/3 x cubed, plus 1/2 x squared. Where are y'all? Plus 2x. What about this? The 2, bring it out front. 1 over x minus 1. What's the antiderivative of 1 over x minus 1? It looks a lot like 1 over u, doesn't it? What's the antiderivative of 1 over u? ln. So ln x minus 1. Do you all agree with this? The 2 comes out. Because remember we were talking about earlier, you know, you have to be careful. This linear expression right here has a 1 in front of it, so we don't have to scale anything out on the outside. It's just 1 over u, so the antiderivative is natural log. Plus c, and I'm done. Well, that wasn't so bad, was it? A little long division, we're in business. Nobody has any questions? I haven't really gone around the room today. I've just kind of asked for feedback. Are y'all ready to be put on the spot yet? They must get harder, right? All right, let's look at the next one. Now, when I started this section where I said rational functions, I said we're going to do this partial fractions thing, and there's 2 steps. Like the first step is to look at the degree, right? And then you might have to use long division, then you move on to the next step. In this problem, we had to use long division, right? We never had to go to the next step because when we used long division, what was there, we could integrate, right? So we didn't need like that next step that I showed you was like all that crap in there. We didn't need any of that because we could handle it. This one won't work that way. So let's see what happens. You look at it. It's a rational function, right? Polynomial divided by a polynomial. The degree of the numerator is 2, right? Degree of denominator is 3, so that's less than this one. Do we do long division when it's that way? No. So we are not doing long division. So what do we do? Right? And that's where the next step comes in. So what the next step says is that what you're going to do is look at the denominator and you're going to factor it. So now look at the denominator and try and factor. I believe it's written up here. Let me see what it says for the notes. Yeah, see, it's already assuming you've factored it. So factor first. Okay, I'm factoring first. So is there anything I can factor here? Just pull an x out. You'd be left with 2x squared plus 3x minus 2 dx. Agreed? That's just if I pull an x out of the bottom. Can you factor this? Because that's a trinomial, isn't it? Does that factor? Or is it irreducible? So let's see. I'm thinking through here. How do you factor? I'm wondering how you factor something like this. Do you like guess and check type thing? You do it mentally? Did you somehow get to Cal 2 and you still can't factor? What's your story? Is that right? 2x squared plus 4x minus x minus 2. That works? All right. You have to be able to do that. And that's a prerequisite for my 1414 class that they can do that. So I'm just giving you a heads up. You've got to be able to factor a trinomial. Whatever method it is, you've got to be able to do it here. So can I rewrite this now? Factoring, your favorite F word, right? Oh, yeah, I believe that. What is this? Plus and then minus 1, is that right? All right, so what we did, recap, looked at this, said, oh, no long division is necessary. Look at the denominator, factor it completely. If this factors, okay, if it factors, which it did, then we're going to move on. If this doesn't factor, we will also move on. We'll have a different way of doing it. But if you mess up, if you think this is not factorable when it is, it's going to be a disaster for you. You can't be like, well, you know what, I'm going to act like that doesn't factor and see what happens. If it factors, you have to be able to break it down. Does that make sense? Because you'll run into trouble later when you're trying to do something to it. All right. All right. So now let's get into some language here. When you multiply things together, they're called factors, yes? So I have 1, 2, 3 factors here, don't I, in the denominator? They are all different, aren't they? They're all different factors. This is x, this is 2x minus 1, this is x plus 2. Those are all different factors, right? So each one of these factors, each one is called a distinct linear factor. It's called a distinct linear factor because, first of all, it's linear, right? That's a linear expression in x. It's a factor because it was ripped apart and it's part of this multiplication, so it's a factor. It's distinct because it's different than all the others in the denominator, right? How many distinct linear factors do we have? We have 3 distinct linear factors. So in this problem, there are 3 distinct linear factors. So that is an example of one of them, but each one of these is a distinct linear factor. We got it? Now, whenever you have distinct linear factors, what we're going to try and do is rewrite this expression. We're going to try and rewrite it in a certain way. And I think to motivate the idea, what I'm